Welcome. Find a comfortable position. Let your body settle and allow your breathing to slow. Tonight we are going to drift gently through the world of algebra, one of the oldest and most quietly beautiful branches of mathematics. You do not need to solve anything tonight. You do not need to remember any of it. Simply let the words wash over you like a slow, warm river. Algebra is at its heart the language of relationships. It asks a simple question. If we know some things, what can we figure out about the things we do not know yet? In its simplest form, thousands of years ago, it was not written in letters and symbols. It was written in words, long, careful sentences describing problems about grain and silver and the dividing of land. Over centuries, mathematicians from Babylon, Egypt, Greece, India, Persia, and beyond slowly shaped these word problems into the elegant, symbolic language we recognize today. The story of algebra is the story of human curiosity, patience, persistent, and quietly determined to find order in the world. So let us begin at the very beginning. Let your eyes close softly. Let the numbers and the letters float past like leaves on a still river. There is nowhere you need to be tonight. There is nothing you need to do. Just listen. We travel back nearly 4,000 years ago to the flat, sun-baked plains of the ancient Mesopotamia, the land between Tigris and the Euphrates rivers, in what is now modern Iraq. Here in the great cities of Babylon and Nepal and Ur, a civilization flourished that was deeply in love with numbers. The Babylonians wrote on clay tablets. They pressed a wedge-shaped reed called a stylus into soft clay, leaving small triangular marks. These marks formed a writing system called cuneiform, and among the thousands of cuneiform tablets that the archaeologists have unearthed over centuries, many of them, a surprising number, are mathematical in nature. One of the most famous is known as the Plimpton 322, discovered in the early 20th century and now housed at Columbia University. This tablet 322, dating to around 1800 BCE, contains columns of numbers that appear to list what we would today call Pythagorean triplets. Sets of three numbers where two squares added together make another square. The Babylonians were exploring deep mathematical territory more than 1,000 years before the Greek philosopher Pythagoras was born. But it is another type of tablet that concerns us most tonight. The Babylonians left behind a treasure love of problem tablets, exercises designed to teach students how to find unknown quantities. A typical problem might read something like this. I have a field. Its length is 7 more than its width. The area of the field is 60. What are the length and the width? What are the sizes of the length and the width? This is, in essence, an algebraic problem. There is an unknown, there is a relationship, and there is a method of finding the answer. The Babylonians solved these problems using a procedure they called completing the square, a technique that remarkably we still teach in algebra classrooms today. The Babylonian mathematicians worked in a number system based on 60, and we call base 60 or sexagesimal. This is why we still divide an hour into 60 minutes and a minute into 60 seconds. The Babylonians gave us that. Their number system was extraordinarily sophisticated, and their algebra, though expressed entirely in words and without any symbolic notation, could handle quadratic equations, problems involving squares of unknown quantities, with practiced ease. Imagine a student in a Babylonian school sitting cross-legged on a mud brick floor, smoothing a fresh clay tablet with careful hands, pressing each mark deliberately, working through problem after problem under the guidance of a scribe teacher. The classroom would have been quiet. The sound of reed and clay, the smell of dust and the distant river. Mathematics learned in stillness 4,000 years ago. Across the desert, along the banks of the Nile, another great civilization was doing mathematics of its own kind. The ancient Egyptians also left us a mathematical papier, fragile sheets of dried reed paper covered in a hierarchic script, the cursive form of hieroglyphics used for everyday writing. The most famous of this is the Rhind mathematical papyrus, named for the Scottish antiquarian Alexander Henry Rhind, who purchased it in Luxor in 1858. It was copied around 1550 BCE by a scribe named Ahmes, who noted that he was copying from an older document, suggesting the mathematical knowledge it contained was already ancient even then. The Rhind papyrus contains 84 problems. Some concern geometry, the areas of circles and triangles, the slopes of pyramids. Others are what we would recognize as algebraic. Problem 24 of the papyrus, for instance, translates roughly as a quantity together with its seventh makes 19th. What is the quantity? In modern notation, we would write this as x plus x divided by 7 equals 19. The Egyptian scribe solves this using a method called false position, a method that feels almost playful. He guesses an answer first. Let us say the quantity is 7, because 7 divides evenly. Then he checks. 7 plus 1/7 of 7 equals 8. But the problem wants 19, not 8. So he scales his guess up by the ratio of 19 to 8. It is elegant, it is indirect, and it works. The Egyptians did not think of their problems in terms of abstract unknowns. They used the word aha, meaning heap or quantity, to refer to the unknown value. Yes, the unknown value was known as aha. The unknown was a heap, something to be found, the thing, sifted out, measured. There is something wonderfully concrete about that image. Mathematics as a kind of digging, as a kind of patient excavation. As we move from Mesopotamia and Egypt into the Mediterranean world of ancient Greece, we encounter a fascinating shift. The Greeks were not primarily interested in practical calculations. They were philosophers, lovers of wisdom, and they approached mathematics with different questions in mind. Not just how, but why. The greatest monument of Greek mathematics is Euclid's Elements. Very famous book, written around 300 BCE in the city of Alexandria. This extraordinary work in 19 volumes lays out the foundations of geometry with logical rigor that was unprecedented in the ancient world. Euclid begins with a small number of definitions and postulates, basic assumed truths. And from these, he derives hundreds of theorems by pure logical deduction. What does this have to do with algebra? More than it might first appear. Euclid's second book contains what historians call geometric algebra, algebraic relationships expressed as relationships between geometric shapes rather than between numbers. For instance, Euclid proves what we would today write as a plus b all squared equals a squared plus 2 times ab plus b squared. Not by multiplying brackets, but by drawing a square of a side a plus b and showing how it can be divided into 4 regions. The Greek preference for geometry over arithmetic meant that their algebra was always spatial in nature. It was always visual. An unknown quantity was not just a number, it was length. A product of 2 quantities was not just a number either, it was an area. This geometric mode of thinking shaped European mathematicians for nearly 2,000 years. The figure who comes closest in the ancient Greek to Pythagoras, to what we would call an algebraist in the modern sense of algebra, is Diophantus of Alexandria, who lived, we believe, sometime in the 3rd century CE. Very little is known about his life. There is a charming riddle that has come down through history, supposedly inscribed on his grave, from which we can calculate that he lived to the age of 84. That is the Diophantus of Alexandria. Diophantus wrote a work called Arithmetica, of which 6 books survive. In these books, he poses and solves an extraordinary variety of problems involving unknown quantities. He invented For the first time in the Western mathematical tradition, a kind of symbolic shorthand abbreviations for the unknown, for its square, its cube, and so on. This proto-symbolic system is a crucial step on the long road toward modern algebra notation. The problems in the Arithmetica are almost entirely what we now call indeterminate. They do not have a single unique answer, but potentially many. Diophantus, however, typically solve rational solutions, fractions, and often found just one. This type of problem, seeking a whole number of rational solutions to polynomial equations, is called Diophantine analysis today in his honor. One of the most famous episodes in the history of mathematics involves the Arithmetica. In the 17th century, a French lawyer and an amateur mathematician named Pierre de Fermat was reading his copy of Diophantus, a translation with commentary, and in the margin next to a problem about writing a number as the sum of two squares, he wrote a tantalizing note. He claimed to have discovered a remarkable proof that no equation of the form x to the n plus y to the n equals z to the n has any whole number solutions where n is greater than 2. Meaning that there is no way that you can solve x exponent n plus y exponent n equals to z exponent n. He says there's no solutions for that, and here's a proof. But he wrote the margin was too small to contain the proof. That's what he said, but this margin is too small for me to show the proof. The marginal node became one of the most famous unsolved problems in the history of mathematics. It was known as the famous last theorem, and it was not proved until 1995 when the British mathematician Andrew Wiles finally succeeded after 7 years of secret work. An algebraic problem planted in the margins of an ancient Greek text, waiting more than 3 centuries to be resolved. We now come to the most important chapter in the history of algebra, the moment when algebra becomes, for the first time, a discipline of its own right with its own name and its own book. The scene in Baghdad in the early 9th century CE, the Abbasid Caliphate is at the height of its power, and the city of Baghdad is the intellectual capital of the world. The Caliph al-Mamam has established the House of Wisdom, Bait al-Hikmah, a great center of learning where scholars translate Greek, Indian, and Persian texts into Arabic, and where original research in mathematics, astronomy, medicine, and philosophy flourishes. Among scholars working at the House of Wisdom is a man named Muhammad ibn Musa al-Khwarizmi. We do not know exactly when he was born or when he died, but he worked during the reign of al-Mamam in the first half of the 9th century. He was a mathematician, an astronomer, and a geographer, and he wrote a book that would change the world. The book is called Kitab al-Mukhtasar fi Sahib Algebra wal Mukhbala, which translate roughly as the compendious book on calculation by completion and balancing. The word Algebra in the title means completion or restoration. The operation of moving a subtracted term to the other side of an equation. And it is this word, algebra, that gives us the word algebra. Algebra. Al-Khwarizmi's book is not primarily about solving abstract puzzles. It is a practical manual written, as he states in the preface, to assist people in matters of inheritance, legacies, land, measurement, trade, and all the everyday transactions of human life. And yet, in setting out the methods of solving equations systematically, Al-Khwarizmi lays the foundation for all the algebra that would follow. He classifies equations into 6 types based on the combinations of squares, roots, numbers, and numbers they involve. What would today write as x squared equals 6x, or x squared plus 10 equals 7x. For each type, he gives a method of solution illustrated with examples of geometric proofs. A bow, perhaps, to the Greek tradition of geometric justification. Al-Khwarizmi writes entirely in words. There are no symbols in his algebra. The unknown quantity is simply called the thing. In Arabic, al-shay. When this was later translated into Latin, al-shay was sometimes rendered as res, the Latin word for a thing, and sometimes translated as shay. Some historians believe this is how the letter X came to represent the unknown quantity. A very long journey from the Arabic word for a thing through medieval Latin translation to the X that every algebra student knows today. Al-Khwarizmi's name also left its mark on the language of mathematics when his works were translated into Latin in the 12th century. His name was rendered as algorithmi. And from this we get the word algorithm, which today refers to any step-by-step procedure for solving a problem. It's an algorithm. His name is embedded in the foundations of modern computer science. Al-Khwarizmi was not working alone. The Islamic world of the 9th through 14th centuries produced a remarkable galaxy of mathematical talent, each building on the work of those who came before. Tabit ibn Qurra, a scholar from the city of Haran, is what is now southern Turkey, worked in Baghdad in the late 19th century. He translated Greek mathematical texts with great care and made original contributions to algebra and number theory. His work on amicable numbers, pairs of numbers, where each is the sum of the proper divisors of the other, was centuries ahead of time. Abu Kamil, an Egyptian mathematician of the late 9th century, took Al-Khwarizmi's work and extended. He solved more complex equations, worked with irrational numbers with greater ease, and wrote problems involving multiple unknowns. His algebra, in many ways, more sophisticated than his predecessors, and he served as an important bridge to later European mathematics. Omar Khayyam, known to English readers primarily as a poet, through Edward Fitzgerald, a romantic translation of his Rubaiyat, was also one of the greatest mathematicians of the 11th century. His algebraic work tackled cubic equations involving the cube of an unknown, and he solved them using geometric constructions involving the intersection of the conic sections, parabolas, and hyperbolas drawn in the sand, their crossing points marking the solutions to equations. Khayyam worked in the city of Isfahan in what is now Iran under the patronage Seljuk Sultan Malik Shah. He formed the Persian calendar, producing an astronomical calendar of extraordinary accuracy. He speculated, ahead of his time, that a fully algebraic solution to cubic equations, not just a geometric one, might be possible. It was not until the 16th century in Renaissance Italy that this would be achieved. While the Islamic world was building its algebraic tradition partly on Greek foundations, mathematicians on the Indian subcontinent were developing their own rich mathematical culture, often in surprising independence. Brahmagupta of India, a 7th century mathematician and astronomer from the city of Binmal in what is now known as Rajasthan, India, wrote the Brahmasputra Stihanta in 628 CE. This work contains some of the most original mathematics of the ancient world. Brahmagupta gives rules for the arithmetic with negative numbers, treating deaths as negative quantities, and he formulates rules for what we would call operations with zero. Though some of his statements about division by zero were later shown to be very problematic. Most remarkably for our purposes, Brahmagupta tackles indeterminate equations with more unknowns than equations, which therefore have many solutions. His analysis of what we now call Pell's equation, finding integer solutions to x squared minus n times y squared equals 1, where n is a given number, was deep and sophisticated. A full 1,000 years before European mathematicians independently discovered the problem. Brahmagupta writes his mathematics in verse, compact, metrically structured, Sanskrit stanzas that would be memorized. This was common in the Indian tradition, where oral transmission of knowledge was highly valued. Imagine the mathematics embedded in poetry, passed from teacher to student in chanted recitation under the shade of a mango tree. A later Indian mathematician who also serves and also deserves our quiet attention is Bhaskara II, who lived in the 12th century. His great work, the Lilavati, is named according to a touching legend after his daughter. The legend says that Bhaskara calculated an auspicious moment for his daughter's wedding by means of a water clock, a vessel with a small hole through which water slowly flowed. But somehow Lilavati's curiosity upset the clock. The auspicious moment passed unmarked, and the wedding never took place. To console her, Bhaskara wrote her a book of mathematics, filing it with affectionate problems addressed directly to her. "Oh, Lilavati, tell me quickly." The Lilavati covers arithmetic, algebra, and geometry in a warm conversational style that is quite unlike the dry formality of most mathematical texts. It was enormously popular and influential throughout the Indian subcontinent for centuries. For several centuries after the fall of the Western Roman Empire, mathematical knowledge in Europe was relatively limited. But beginning in the 12th century, a great movement of translation got underway, centered on cities like Toledo in Spain and Palermo in Sicily, cities where Latin, Arabic, and Greek-speaking scholars lived and worked in proximity. Scholars like Gerard of Cremona, an Italian who spent decades in Toledo translating Arabic texts into Latin, brought the works of Al-Khwarizmi, Euclid, and many others into the Latin-speaking world of medieval Europe. Al-Khwarizmi's Algebra appeared in Latin as Liber Algebrae et Al-Muqabola. The word algebra, arriving in Latin from Arabic, began its journey into all the European languages. One of the most significant figures in the transmission of Islamic mathematics to Europe was Leonardo of Pisa, better known today by the nickname Fibonacci, meaning son of Bonacio, born around 1107. Fibonacci grew up in the North African port city of Bugia, where his father was a customs official for the Italian merchants. He studied with Arab mathematicians and became deeply familiar with the Hindu-Arabic numeral system, the system of 10 digits, including 0, arranged positionally, that we use today. In the year 1202, Fibonacci published his great work, the Liber Abaci, the Book of Calculations. It introduced the Hindu-Arabic numerals to European audiences with systematic thoroughness, demonstrating their enormous practical advantages over the cumbersome Roman numeral system then in use. The Liber Abaci also contains extensive sections on algebra, drawn from Al-Khwarizmi and others. Fibonacci's work planted seeds that would take centuries to fully flower. By the 16th century, Italian mathematicians had mastered the solution of quadratic equations involving squares of the unknown, and were straining to go further. The great prize was the cubic equation, an equation involving the cube of the unknown, and it fell to a colorful and contentious group of Italian mathematicians to seize it. The story is tangled and dramatic, involving priorities, disputes, public contests, and accusations of broken oaths. The central figures are Scipione del Ferro, a professor of mathematics in Bologna, Niccolo Fontana, known as Tartaglia, meaning the stammer, a self-taught mathematician from Brescia, and Girolamo Cardano, a brilliant, unstable polymath who was simultaneously a physician, mathematician, philosopher, and compulsive gambler. Del Ferro, around 1515, discovered a method for solving one type of cubic equation. He kept it a secret. Mathematical knowledge was a professional asset in an era when scholars competed in public problem-solving contests. On his deathbed, he passed the secret to a student. Tartaglia independently rediscovered the method around 1535 and won a famous public contest against Del Ferro's student. He too kept the method secret, but Cardano charmed Tartaglia into sharing it with him under a solemn oath of secrecy. Then Cardano, hearing that Del Ferro had discovered the method first, decided, reasoning that the original discoverer had not sworn him to secrecy, to publish the formula in his great book, the Ars Magna, in 1545. The Ars Magna is a landmark in the history of algebra. It presents, for the first time in print, solutions, general solutions to cubic and quartic equations. Equations involving cubes and fourth powers of the unknown. Cardano's student Lodovico Ferrari had solved the quartic, and Cardano included that solution too. The book represents the most significant advance in algebra since Al-Khwarizmi 7 centuries earlier. The Ars Magna also contains something philosophically startling. In the course of solving certain cubic equations, Cardano encountered the square root of negative numbers, what we would now call imaginary numbers. He found these quantities perplexing and called them sophistic, fictitious, meaningless. But he kept them in his calculations, noting that if you just followed the rules and kept going, the imaginary pieces cancelled out and you arrived at the real answer. The mysterious, the impossible was somehow useful. This strange observation planted a seed that would, over the next 3 centuries, grow into the theory of complex numbers, one of the most beautiful structures in all of mathematics. The algebra of Al-Khwarizmi, Fibonacci, and even Cardano was still largely rhetorical, expressed in words and abbreviated words, not in clean symbolic language we use today. The great transformation to fully symbolic algebra was accomplished over the 16th and 17th centuries through the work of several mathematicians. François Viard, a French lawyer and amateur mathematician working in the late 16th century, made a crucial innovation. He used letters not just for unknown quantities, as Diophantus had done before, but also for known quantities. This might seem like a small step, but it was profound. Suddenly you would write formulas that describe the general relationship between quantities, not just the solution to a specific problem. Algebra became, for the first time, truly general. François Viard called his new approach logistique speciosa, species logistic, meaning a calculation using types or species of quantity rather than specific numbers. He used vowels for unknown quantities and consonants for known quantities. The letters were different from ours, but the spirit was the same. You could write a formula once and it would work for any numbers you substituted into it. René Descartes, the French philosopher mathematician who gave us the famous cogito ergo sum, I think, therefore I am, also made critical contributions to the algebraic notation in his 1637 work, La Géométrie. It is Descartes who established the conversion still with us today, using letters from the end of the alphabet X, Y, Z for unknowns, and letters from the beginning A, B, C for known consonants. His notation was clean, economical, and powerful, and it was widely adopted. René Descartes. Descartes also achieved something even more revolutionary. He fused algebra and geometry together. His invention of the coordinate plane, what we now call the Cartesian plane, in his honor allowed every algebraic equation to be represented as a geometric curve, and every geometric curve to be described by an algebraic equation. The two great streams of ancient mathematics, the arithmetic tradition of the Babylonians and the geometric tradition of the Greeks, flowed together at last into a single river. The 17th century brought the invention of calculus independently and nearly simultaneously by Isaac Newton in England and Gottfried Wilhelm Leibniz in Germany. Independently. Calculus is, in a sense, algebra applied to quantities that are continuously changing. It required the algebraic notation that Viet and Descartes had developed, and it pushed that notation to its limits and beyond. Newton thought of algebra as a universal arithmetic, a tool for reasoning about quantities in general, not just specific numbers. His methods of fluxions, his version of calculus, was developed using algebra ideas about infinite series and limits. Leibniz, independently arriving at the same ideas, developed a notation for calculus that was so elegant and convenient that it's still the notation we use today, the integral sign, the differential d. By the end of the 17th century, algebra had been transformed. It was no longer primarily a collection of techniques for solving specific equations. It had become a language, a universal language for expressing and exploring mathematical relationships of all kinds. And the greatest discoveries of the 18th and 19th centuries would be made in this language. The 19th century saw algebra undergo another profound transformation, one that took it from the study of equations to the study of abstract structures. Two figures stand out at the beginning of this transformation: Carl Friedrich Gauss and Évariste Galois. Friedrich Gauss, the prince of mathematicians, as he was sometimes called, published his doctoral dissertation in 1799 at the age of 22. It provided the first complete proof of the fundamental theorem of algebra, the statement that every polynomial equation with complex number coefficient has at least one complex number solution. It was a theorem that had been assumed for centuries but never rigorously proved. Gauss proved it, and then proved it again and again and again and again and again and again, offering 4 different proofs during his lifetime, each from a different angle. The story of Évariste Galois is one of the most poignant in the history of mathematics. He was born in 1811 near Paris, a brilliant and turbulent young man who twice failed the entrance examination for the École Polytechnique, reportedly because he refused to explain his reasoning to the examiners, considering it was obvious, and who was repeatedly imprisoned for his radical political activities. On the 9th of May, 29th, 1832, knowing that he was to fight a duel the following morning, a duel from which he apparently did not expect to return, the 20-year-old Galois sat up all night writing furiously, trying to record his mathematical ideas before it was too late. He was right not to return from the duel. He did not. He died the following day at the age of 20. The papers he left behind, when they were eventually understood and published, revealed the theory of breathtaking originality. Galois had found the keys to understanding why the cubic and quartic equations could be solved by formulas involving radicals, square roots, cube roots, while the general quintic equation involving the fifth power of the unknown could not. His method introduced the concept of a group, a set of elements with an operation satisfying certain abstract properties, and showed how the structure of this group determined the solvability of the equation. Galois theory is today a cornerstone of modern algebra. It is also the origin of group theory. The mathematical theory of symmetry, which has become one of the most powerful tools in physics, chemistry, and mathematics itself. All of it from the fervid midnight writing of a brilliant young man who knew he would not survive to see the morning. The 19th century brought many other abstract structures to light alongside the group. Rings, fields, vectors, spaces, modules. Each was a collection of objects with operations satisfying specified axioms, and each provided a framework for understanding large swaths of mathematics at once. Emil Noether, a German mathematician working in the early 20th century, was perhaps the greatest algebraist of her era. Her 1921 paper on the theory of ideals in rings provided the framework that unified and generalized enormous portions of algebra. She worked at the University of Göttingen, but as a woman, she initially could not hold an official position. She lectured under the name of a male colleague for years. Her colleague recognized her genius. The institution resisted it. When the Nazis came to power in 1933, Noether, who was Jewish, was dismissed from her position. She emigrated to the United States and took a position at Bryn Mawr College, where she worked until her sudden death in 1935 at the age of 53. Albert Einstein, in an obituary in the New York Times, called her the most significant creative mathematical genius thus far produced. And now, as we drift toward the final part of our journey, let us revisit some of the core ideas of algebra itself. Not as problems to be solved, but as ideas to be gently absorbed, like warmth from a quiet lamp. The most fundamental idea in algebra is the variable, a symbol, usually a letter, that stands in for a quantity we do not know yet, or a quantity that can take different values. When we write x, we are leaving a space, a placeholder for something we are about to find, or something that can vary. This idea, so simple and so powerful, was not obvious. It took thousands of years of mathematical development before anyone wrote it down clearly. The Babylonians had their thing. The Egyptians had their heap. Diophantus had his abbreviations. But the fully abstract variable, a letter could stand for any number at all, had to wait for Fiat and Descartes. An equation is a statement of balance. When we write two expressions with an equal sign between them, we are saying these two things are the same. They weigh the same in some abstract mathematical sense. Whatever we do to one side of the equation, we must do to the other to preserve the balance. This is the fundamental rule of equation solving. Add the same thing to both sides. Subtract the same thing from both sides. Multiply both sides by the same number. Divide both sides by the same number. Keep the scales level. Keep the equation true. And gradually, step by step, you peel away the layers, isolating the unknown, finding what it must be. A polynomial is an expression built from a variable or variables using only addition, subtraction, multiplication, and non-negative whole number powers. The simplest polynomials are linear. They involve only one variable, the variable itself, to the first power. Expressions like 3x plus 7 or 2x minus 5. This produces straight lines when graphed on the coordinate plane, the Cartesian plane. Quadratic polynomials involve the square of the variable. Expressions like x squared plus 3, x minus 4, x squared plus 2x plus 8. These produce parabolas, the graceful U-shaped curves that describe the path of a thrown ball, the shape of a satellite dish, the cross-section of a headlight reflector. Cubics involve the cube. Quartics involve the fourth power. Each brings new complexity. Each brings new shapes. Each brings new layers to the solution. The fundamental theorem of algebra, the one Gauss proved, tells us that a polynomial of degree n always has n solutions, counting complex solutions and repeated solutions appropriately. A quadratic always has 2 solutions. A cubic always has 3 solutions. A polynomial of degree 10 always has 10 solutions. The universe of solutions is neatly, perfectly counted by the degree of the polynomial. A function is a rule that assigns to each input exactly one output. We write f of x to mean the output of the function of f when the input is x. Functions are everywhere. In the natural world, in economics, in engineering, in everyday life. The amount of money in a savings account is a function of time. The temperature outside is a function of the time of the day, or the time of day. The distance a car has traveled is a function of its speed and the time it has been moving. Algebra gives us a language for describing functions, precisely for combining them, transforming them, inventing them. inverting them, finding the function that undoes what a given function does. The algebra of function is the engine that drives calculus. And through calculus, it drives most of the modern science and engineering. We have traveled a long way tonight. From the clay tablets of Babylon, pressed with wedge-shaped reeds on the banks of the Euphrates 4,000 years ago, through the papyrus scrolls of Egypt, the geometric proofs of Greece, the lyrical Sanskrit verses of India, we have walked through the sunlit courtyards of the House of Wisdom in Baghdad, where Al-Khwarizmi sat with his reed pen and wrote the word that would become algebra. We have passed through the dramatic contents and contest of Renaissance Italy, through the cool clarity of Descartes and the burning midnight pages of Galore. We have seen algebra grow from practical to for dividing estates and measuring fields into one of the most abstract and powerful languages human beings have ever invented. A language for describing patterns in their purest form. A language that speaks not about this specific number or that specific shape, but about all numbers, about all shapes, about all relationships that satisfy a given set of rules. There is something dreamlike about algebra. When you think about it, it works with symbols, marks on paper, or clay, or sand that stand for things we cannot see or touch. An X is not a thing. A function is not a thing. A group is not a thing. And yet, by reasoning carefully about these abstract entities, we have built bridges, cured diseases, sent probes to the edge of the solar system, and begun to understand the deeper structure of the universe. Mathematics is perhaps the longest dream humanity has ever shared. A dream that has begun the agricultural villages of ancient Mesopotamia, where someone first noticed that the same problem kept recurring. A different field, a different harvest, but the same underlying relationship. And the person thought, there must be a better way to think about this. that thought, quiet, patient, curious, echoed down through 4,000 years and 10,000 mathematicians and hundreds cultures and a dozen languages, and became algebra. And algebra became the language of science. And science became the engine of modern world. All of that beginning with someone pressing a stick into wet clay beside a river in the morning light, asking, if I know some things, what else can I know? Let that question rest now, quiet as a stone at the bottom of a deep, still pool. You are doing wonderfully. Your breathing is slow and easy. The numbers are drifting away, softly like smoke in still air. There is only the gentle sound of the night and the faint warmth of mathematics. All around you. Rest now. Sleep.